We now use displacement formulation to get the internal stresses, strains, and displacement of a cylindrical structure cantilevering out, having a length L, and subjected to a tension load P. This problem is similar to the torsion problem we discussed previously. So instead of torque tau, now we have a tension load applied at the free end of the cantilevered cylinder. So this problem we will solve using displacement formulation. So first of all, we will find out displacement, again, then the strains, and finally stresses. So this is the same method we followed previously in the case of a torsion of a cylinder. So let us start by assessing the displacements. We have three displacement, UR, U theta, and UZ. All three of them in general are function of r, theta, and z. Now let us rule out some of the variables or displacements. This will depend on our engineering judgment and the type of approximation we want. If we want to look at it more in a more deeper manner, then we will allow some of the variables. However, in this course, we will try to simplify it to the extent that we get the same answers as in our undergraduate courses of mechanics of solids. So the first displacement is UR displacement along the radial direction. And since this cylinder is subjected to load P, therefore we can say that there can't be any dependence of UR on theta. In the previous case, our UR was zero. And the reason it was zero was because of considering the torque causing no radial deformation. In the current case of applied tension load, we will have some UR, and that is because of the Poisson effect. So clearly, if we have a load P applied and we are trying to extend it, there will be some narrowing of this body in the transverse direction, and hence UR will come into play. This UR will not be dependent on the theta variable because the load applied has got no bearing on theta. Remembering that theta is the orientation of a piece chopped out from a cylindrical body, and the orientation of this piece is with respect to some reference axis. So essentially, we are saying that UR will be constant for all the theta. So theta can be starting from 0 till 2 pi, and UR at a particular region will be independent of theta. Now, the third parameter or the third variable is Z. Conceptually speaking, UR should be dependent on Z. In general, this change, this variation, or this dependence on Z can be neglected because the variation of Poisson effect along the length of this cylinder would be relatively small. So we can neglect it. The second displacement variable is U theta. U theta is a function of R, theta, and Z. The current condition of axial load application, there is a less tendency of circumferential displacement. So therefore, we assume U theta equal to 0. Finally, we have UZ, which is again function of R, theta, and Z. Surely UZ will be dependent on the Z coordinate. So our longitudinal displacement will be varying with the Z coordinate. UZ again won't be dependent on theta or on the rotation of any cross section. So if we consider again the cylinder being divided into longitudinal and radial lines, then as we are moving away from the support, we can assume that the uz in our case won't cause any rotation of the radial circles. Uz can be a function of radius r, but the change in r causing some displacement in uz will be very small. However, as we discussed, due to the Saint Venant principle, if we go further from the support, then this influence can be reduced and the disturbance reduces, and we have got the stress flow more uniform. Thus, we can ignore the dependence of uz on radius r. That finally gives us ur a function of r, u theta equal to 0, uz a function of z. We'll follow the same procedure as in the torsion problem and try to develop the answer. So our displacement function or displacement vector is equal to u of r, 0, and w of z. In the case of torsion, we had one function dependent on two variables. In the current question, we have two displacement functions and they are dependent on single variables. So this can be treated as a problem of ordinary differential equations. So again, the first step is to find out our strains. So the equations which we developed look like these ones. Plugging the values in these equations, and we will get the strain equal to u dash, u by r, and w dash. So we will have only a diagonal term, and that means that we have the functions dependent only on one variable. After this, we'll plug the values in stresses and we will try to find out the stress. So the stress tensor will also come out to be a diagonal one. Sigma 1 1 is lambda plus 2 mu in small brackets times u prime plus lambda times small bracket u by r plus w dash. Then sigma 2 2 is lambda plus 2 mu in small bracket times u by r plus lambda in small bracket u prime plus w prime, and sigma 3 3 is lambda plus 2 mu w prime plus lambda small bracket u prime plus u by r. After this, we'll plug the values in equilibrium equations. So we derived three equilibrium equations. Plugging values in these three equations, we get lambda plus 2 mu u double prime plus lambda u prime by r minus u by r square plus 2 mu by r small bracket u prime minus u by r. The second equation will come out to be 0, and the third equation will come out to be lambda plus 2 mu in small bracket times w prime. Now this first equation again is the Euler-Cauchy equation which we discussed in the case of torsion of the cylinder. So we can solve it, and again we get u of r equal to c1 r plus c2 by r. Again, at r is equal to 0, this term can become infinite, so therefore we can omit this term and we are left with u1r. We can solve this third equation and we will get wz equal to az plus b. So this is a simple first order differential equation, and it can be easily solved, and this is the solution. Again, wz is equal to 0 at z is equal to 0, so that will give b equal to 0. So ur is c1r, wz is az. Plugging values back in our strain equation, we find that strain rr is equal to c, strain theta theta equal to c, and strain zz equal to a. We can then plug the values in our stress equations and find the value of stresses. So sigma RR is equal to 2 small bracket lambda plus mu times C plus lambda A. Sigma theta theta is equal to 2 times small bracket lambda plus mu times C plus lambda A, and sigma zz is equal to small bracket lambda plus 2 mu times A plus 2 lambda C. Please note that UR is assumed to be C time R, and based on that, epsilon R and epsilon theta theta are derived. C is the constant which is unknown, so we can write that that epsilon RR at the surface, assuming that surface is at radius C bar, is equal to 0, as there is no external traction on the surface. Using that, we can get epsilon RR is equal to 0 and make this term equal to 0. Noting that there is no radius term in this equation. From here, C can be worked out. We know from our previous discussion that mu is E by 2 small bracket 1 plus nu. Lambda is E lambda by 1 plus nu by 1 minus 2 nu. So epsilon ZZ in the end will come out to be lambda plus 2 mu times A minus lambda square by lambda plus mu times A. Hence, the value of C is plugged into epsilon ZZ, and we get epsilon ZZ equal to mu small bracket 3 lambda plus 2 mu divided by small bracket lambda plus mu times A, or we call this modulus of elasticity E times A. Now the only constant left is A, and again A is dependent on boundary conditions. We can have two different types of boundary condition. Either we apply end displacement or either we apply end force. In the case of end displacement, we can rewrite uz as equal to az, and this is what we derived previously. Wz is equal to az. Now, if we can assume that the displacement applied is A time L. So the applied displacement is some proportion times L, and this proportion factor is strain. Equating these two, we can get A is equal to delta by L. In the case of end force, we can have P equal to sigma zz time dA. So we assume that load P is applied and that P is distributed all over the cross-sectional area at the end of the cantilever, and the distribution is uniform. So in other words, load P is distributed uniformly at the end of the cantilever. That makes P equal to epsilon ZZ times dA, and that is equal to E time A. So sigma ZZ we worked out as EA, and integral of dA come out to be an area. Noticing that epsilon ZZ will come out of the integral because it is a constant, or the two factors involved E and A, they are not independent of dA. From here, we get A is equal to P by EA. We can also write delta is equal to A times L, and that is equal to PL over AE. Delta is equal to PL over AE is actually the total deformation